Hello everyone. So in the last class, this was the last slide that we were discussing, and it talked about the supramolecular heterosyntons and what role they play in the formation of the crystal lattice of the co-crystal. And we had stopped at a point where we had mentioned the role of Cambridge structured database in identifying the synthons that could be responsible for formation of the co-crystals. So we move forward from here to the next slide. Sorry, so this is the next slide where we were talking about the Cambridge structure database. So in the Cambridge structure based database, there are a couple of options that can help us in identifying the types of structural motifs that are present. By structural motif, we mean a group of functional groups that are involved in the formation of hydrogen bonding or other bondings within the crystal lattice. So there are two ways. One is to use a software called as Conquest, or you can have the motif search technology in the Mercury Cambridge structure database. So what we do in this Cambridge structured database is that we find out the probability of occurrence of a particular synthon in a crystal lattice, which means which are the motifs that are highly likely to be present in the crystal lattice structure. So those are the ones that we should choose so that the formation of the co-crystals can be enhanced, or the probability of formation of the co-crystals can be enhanced. So this probability is calculated by taking a ratio of the actual number of motifs observed in the Cambridge structure database to the number of structures where the motifs could occur. And if we look at the distribution of the motifs with respect to this, the frequency of occurrence is given here. So the highest frequency of occurrence of 60% is given to carboxylic acid oxime, which means if there is a structure or if there is a compound which has this particular set of functional groups, then the probability of these two groups in the formation of the crystal lattice is going to be very likely. So what this can help us in the co-former selection, in the sense that if you know the functional group that is present in your API, so you can pick up a co-former which has a complementary functional group present in it, so that the probability of the formation of the motif increases. So if you have a drug with a carboxylic acid functional group, you could pick up a co-former which has a oxime group present in it, because that has the highest probability of occurrence. But if you pick up for a carboxylic acid a co-former that also has a carboxylic acid, then the probability of occurrence is only 30%. So that's the second way, apart from the delta PK rule, which can be used to choose the co-formers for the formation of the co-crystals. Now, the formation of the co-crystals can be done through various means. So the first and the foremost, most common method that is used at the lab scale is the neat grinding method, wherein you take the drug and the co-former and then grind them in a mortar pestle to get the co-crystal. And the second way is liquid assisted grinding. So here, instead of grinding it neat, you add a very small quantity of solvent into the mortar pestle and then grind it. So this is the most common method that has been reported in literature for screening the formation of the co-crystals. Then there are solution-based methods like solvent evaporation, reaction co-crystallization, cooling co-crystallization, and slurry method. And then there are other methods like spray drying, ultrasound assisted solution co-crystallization, supercritical fluid technology, Koffler method, which is based on the use of hot stage microscopy. So all these methods are possible that can be used for the screening of the co-crystals. As you can very well judge from the list, only few of them are going to be useful at the industrial scale, while rest of them are going to be useful at the lab scale. The characterization of the co-crystals is done in a manner which is very similar to characterization of any new solid form. So you can carry out the thermal characterization using the differential scanning calorimeter, So here is one example of indomethacin saccharin co-crystal. So A is the heating curve of indomethacin, B is that of saccharin, and C is that of the co-crystal. So you can see the co-crystal has a melting point which is in between the melting point of saccharin and indomethacin. This is not always necessary, or this is not always true. Your co-crystal can also have a melting point which is uh, higher than both the ingredient, or it can be lower than the both the ingredients. So all the three possibilities are there. Then obviously you can use the PXRD. When you take the PXRD of the components, that is the drug and the coformer and the co-crystal will give you a unique characteristic diffraction pattern. It is not going to be a simple summation of the diffraction pattern of the drug and the coformer. The reason for this is that co-crystal involves formation of a new crystal lattice, and obviously there will be a unique diffraction pattern that is going to come. In fact, this is one way by which we differentiate between eutectics and co-crystals, because eutectics will give a diffraction pattern which is summation of the two ingredients, whereas co-crystal will give us a unique diffraction pattern. Then the other tools like Raman, single crystal XRD, infrared spectroscopy, solid state NMR, terahertz time domain spectroscopy can also be used on the need basis for the characterization of the co-crystals. Now we come to the important aspect from a pharmaceuticals perspective, that why co-crystal? Why do we want to use the co-crystals when we have so many other solid forms available at our disposal? This is primarily because of the co-crystal's ability to modulate the physicochemical properties of the drug molecules without the need for covalent modification. And because of this, the co-crystals are becoming increasingly uh, popular as well as important. So you can see the co-crystals can modulate all the physicochemical properties like solubility, dissolution rate, hygroscopicity, stability, crystallinity, and the mechanical properties of the APIs. And this can help us in addressing the major goals with respect to the pharmaceutical development. That is, it can change the bioavailability, stability, and manufacturability of the APIs. And additionally, as we have been discussing, the co-crystals give us an opportunity to protect the patent, or extend the protection through the patenting, because they are novel forms. Now we come to the discussion on role of co-crystal in the modulation of physicochemical properties. So the first and foremost property that any pharmaceutical development scientist is trying to address is that of the solubility. And co-crystals have been extensively used for this particular purpose. So here is one example of fluoxetine hydrochloride, fumaric acid, fluoxetine hydrochloride succinic acid co-crystals, and then there is fluoxetine alone, and then there is fluoxetine hydrochloride benzoic acid co-crystal. As you can see in the case of this particular co-crystal, which is the fluoxetine succinic acid co-crystal, there is a shoot up in the solubility, apparent solubility initially, and which then reduces down as the time passes. So this is what is called as a spring effect in the solubility profile of the co-crystal. Similar terminology is also used for the amorphous systems that can also show what we call as the spring effect. So in this diagram, so this is the spring effect shown in the blue curve. Whereas if you have a profile like this, wherein the maximum apparent solubility is sustained over a period of time, then we call this particular effect as the parachute effect. So the co-crystals may exhibit an initial peak concentration followed by an immediate decline called as the spring effect. For example, here in the case of fluoxetine hydrochloride succinic acid, it is a 2:1 co-crystal. This particular curve, which we were referring earlier, in water, it gets converted to less soluble parent form with decline in solubility of fluoxetine hydrochloride, and this shows a clear spring effect. Now, a very important measurement for the co-crystals is to find out their true solubility. and it is many a times very challenging to find the solubility of a co-crystal, as they have a tendency to convert back to the parent forms during the dissolution. Parent forms means this will have a tendency to dissociate to the API and the coformer during the process of dissolution. So a way forward to address this particular issue is to determine what we call as a eutectic constant. Now, eutectic constant is the ratio of concentration of the coformer to that of the drug at the eutectic point, and it is given by this equation, which is shown here, wherein the solubility of the coformer is divided by the solubility of the drug to get the value of the K eutectic. So eutectic point is a point at which the solution is saturated with respect to both the drug as well as the coformer. It is independent of the mass of the each phase at equilibrium and is dependent upon the temperature, pH, solvent, and additives. So we'll further see the significance of determination of the eutectic point with specific reference to the co-crystals. Now, if you add a co-crystal to a saturated drug solution and you slurry it until saturation or equilibration, and then you analyze the solid phase by XRPD or any other solid state characterization technique, then you need to answer this question: are the two solid phases present? And what are those two solid phases that we are referring to? We are referring to the co-crystal as well as the drug. So if the answer to this is yes, which means you are able to characterize leftover drug as well as the co-crystal, then you measure the solubility value of both these using HPLC or any other suitable technique, and then take the ratio of the solubility of the drug divided by the coformer, and this will be called as the K-eutectic. But if only drug is detected in the XRPD, then you add more co-crystal and you slurry until the saturation or equilibration takes place. And in the other scenario, if there is only the co-crystal, then you add the drug and slurry until you get the equilibration. So coformer EU is the concentration of the coformer, and drug EU is the concentration of the drug at the eutectic point. So once you have the K eutectic value for the co-crystal, it gives you very important piece of information, which is shown in this particular slide. So if the K eutectic value for the co-crystal comes to be 1, what it means is that the solubility of the drug and that of the co-crystal is same, which means there is neither a decrease nor an increase in the solubility of the drug as far as the co-crystal is concerned. And the stability of the drug and that of the co-crystal would also be the same. But if the K eutectic is less than 1, it means the co-crystal is less soluble than the parent drug, and co-crystal will be thermodynamically more stable than the drug per se. And if the K eutectic value is greater than 1, then co-crystal is more soluble than the parent drug, and co-crystal is thermodynamically less stable than the API alone. So in terms of the pharmaceutical utilization, a K eutectic value of 2 to 10 is considered to be optimal, because it will provide the desired improvement in the solubility as well as the thermodynamic stability of the co-crystal would be acceptable. Sometimes what happens is that you get a eutectic value of 1000 or even more. In that case, what happens is, although there will be extremely high apparent solubility, but that solubility will be short-lived, because the thermodynamic stability of the co-crystal is so less that the solubility will tend to crash to the solubility of the drug very quickly. So it is not desirable to have a very high K eutectic value, and eutectic values of 2 to 10 are considered to be optimal for designing of the co-crystals. Now coming over to the improvement of hygroscopicity or the moisture stability using the co-crystal approach. So here we'll take it up with the help of one example of caffeine oxalic acid co-crystal, which is formed in the stoichiometry of 2:1. So anhydrous caffeine is not stable and it readily converts to the respective hydrated form because it picks up water. And the hydration stability of the caffeine in one research work was improved by co-crystallization with oxalic acid. So introduction of additional stabilization by hydrogen bonding, which may mean that fewer unsatisfied hydrogen bond donors or acceptors exist in the co-crystals compared to the drug, contributes to better moisture stability or lesser hygroscopicity. So here is the table that shows the hygroscopicity behavior of caffeine and the co-crystal. So this CAF stands for caffeine, and you can see at 98% relative humidity, phase transformation occurs within 1 day for the caffeine. But if you design the co-crystal, then that remains stable even up to 7 weeks period. So this is one example wherein the hygroscopicity profile of caffeine was improved by designing a co-crystal of caffeine with oxalic acid. There are similar other examples in literature. For example, theophylline oxalic acid co-crystals, imatinib mesylate hydroxyurea, and nitrofurantoin para-amino benzoic acid co-crystals. Another example is that of metformin, as you can see here. So this is the DVS profile of metformin shown in the figure A, and you can see at RH values greater than 60, it picks up extremely high values of moisture. So metformin is a highly hygroscopic material, but when you design a co-crystal of metformin with gliclazide, you can see the hygroscopicity behavior improves drastically. So it does not pick up significant amount of moisture even at 80% RH. So this is one good example wherein the hygroscopicity of metformin was decreased by creating a co-crystal with another drug, that is gliclazide. Similarly, the solid state chemical stability was improved for adipofir dipivoxyl. It is a weakly alkaline, it is a drug which shows high degradation in the alkaline environment as compared to that in the acidic environment. So what was done was a co-crystal with saccharine and nicotinamide was created. And if we rank order the total number of impurities formed after 30 days, it was least in the saccharine co-crystal, followed by nicotinamide, followed by the API. The reason that was given is that saccharine might have provided a weakly acidic environment that prevented the hydrolysis and degradation of the drug, whereas nicotinamide is providing relatively basic environment, so there was a greater degradation in this co-crystal, but even then it was better than the pure API. Apart from the pH of the microenvironment, crystal packing and hydrogen bond formation could be other factors that would influence the chemical stability of the adipofir dipivoxyl. Similarly, intrinsic dissolution rate of the drug can be enhanced and sometimes decreased also using the co-crystal. In the case of exemestane with a co-crystal with malic acid, the IDR was not changed drastically and it remained comparable to the parent drug. So this is shown in the first row with a red color box. Various co-crystals of fevaxostat with urea, acetamide, nicotinamide, para-aminobenzoic acid and saccharine were generated. And as you can see, the IDR was much higher in the case of febuxostat. Febuxostat, as you know, is a drug that is used for treatment of gout, and it is a BCS class 2 drug. Similarly, in the case of sulfacetamide, co-crystals with caffeine and isonicotinamide reduce the IDR, whereas that with theophylline improved the IDR. Similarly, there are two other examples of megestrol acetate and nitrofurantoin given in this particular table. So what comes out of this discussion is that you can either increase the IDR using the co-crystals, or it can even decrease depending upon the type of co-former that has been chosen. So it is not always that if you create a co-crystal, you will always see an improvement in solubility. You can also see a decrease in the solubility because of the properties of the coformer. Similarly, the mechanical properties of paracetamol were improved. As you know, paracetamol form 1 has corrugated layers of molecules arranged in the crystal lattice. This we had discussed in one of the previous classes where we were understanding the use of Mercury software, and it is a difficult to compress powder, and it shows high tendency of capping and lamination. However, if you convert the paracetamol to its co-crystals using uh, theophylline, naphthalene, oxalic acid, and phenazine, they show improved compressibility and tabletability as is shown here. Earlier it was showing capping and lamination, but you can see the co-crystals are going to give us extremely good looking tablets. So the co-crystallization produced layered structure similar to form 2 of paracetamol, and this was responsible for improving the tabletability of paracetamol. Bioavailability obviously can be improved by the co-crystal approach because it gives us improvement in the aqueous solubility. And if solubility is the limiting parameter for the oral bioavailability, the co-crystal obviously will show us improvement in the oral bioavailability. So here is one compound called as candidate 1, which was designed as glutaric acid co-crystal, and the initial properties of candidate 1 was it had a extremely low solubility and a pK of the conjugate acid was minus zero point 0.5. So after the designing of the co-crystal, you can see in the dog studies, these are the bioavailability studies in dogs, you can see there is an extremely high improvement in the oral bioavailability from the co-crystals. So this is one example where the co-crystal approach has been used to increase the plasma AUC values, and they were improved by more than 3 times as compared to the candidate 1. Moving over to another slightly different discussion now, which is that how the regulatory how the regulatory agencies classify the co-crystals. Are they considered new chemical entities, or are they considered only polymorphic form? So this is an extremely important aspect from the development perspective, because if some company wants to use a co-crystal